in August 2023, I got you. Do you hear me well?
Yes, of course we do.
Also, it's good. In August 2023, the UN General Assembly proclaimed the International Decade of Sciences for Sustainable Development from 2024 to 2033. The task to lead the preparation and implementation of the activities within the decade was given to UNESCO. In April 2024, the Earth Humanity Coalition was founded as an association of global, regional, and national scientific organizations with the task to prepare and implement, in close cooperation with UNESCO, various initiatives within the overall program of the decade. The World Academy of Art and Science and the Club of Rome were among the founding members of the coalition. The Academy had initiated the Program of Sciences for Sustainable Development, which became a specific initiative of the coalition. These talks on science for human security, which are devoted to the future with fusion energy, is the 9th webinar within the program. The reports on the previous webinars can be found on the WAAS, on the World Academy's website page events. Now, I'm asking Dragoslav Čirić, former Tokamak operation manager within the Joint European Torus, to give the introduction to the webinar and also to moderate the discussion upon the three talks. Dragoslav, please.
Right. So, as Nebojša said, my name is Dragoslav Čirić. I spent more than 30 years on the Joint European Torus, which until recently was one of the biggest tokamaks in the world at various positions, and finished as the JET operations manager, which included also managing of the DT experiments at the end of JET. As you can see from the color of my hair, I am now retired. And I was just asked by my friend Nebojša Nešković, in fact, whether I can organize that. And I thought maybe WAAS talks are well, a good forum, in fact, to, well, have a few words about fusion, because all of us spend quite some time in that field. And the others probably need to know as well. As those webinars normally have quite a wider audience, not only online, but also later on, in fact, as they're recorded, I thought it makes sense, in fact, to go through the short crash course on fusion, just for information. So I'm going to spend about 6 or 7 minutes in doing that, providing that I can find, in fact, where is my presentation, which is always the case. Just a second. Right. So let's start with this straight away. We all know that the world needs clean, safe, and sustainable source of energy for future generation. I mean, we know what's happening now during the Iran war with the energy. What happened in the mid-70s when actually the whole work on fusion really started seriously. And fusion is one of methods of producing energy which fulfills most of these requirements, if not all of them. It relies on the processes which heat the sun and other stars, in which two hydrogen isotopes, deuterium and tritium, collide. And this unstable nucleus decay into the helium nucleus and the neutron, and the difference in the mass between the incoming particles and outgoing particles is there to release a huge amount of energy, in total about 17.6 mega electron volts, which is shared between the neutron with 14 megawatts, 14 MeVs, and helium with about 3.5. Now, those neutrons, they will slow down in the wall of the future fusion reactor, and it will release energy. And when you release energy, you produce heat. Once there is heat, you can produce some steam and to power the turbine and connect everything to an electrical generator. So it looks very simple, but as you will find out, it's actually considerably more complicated. There are certain conditions which have to be fulfilled for the fusion reaction to sustain. Because deuterium and tritium are positively charged particles, they will repel and they need certain energy to fuse, but also we need a certain particle density and also so-called energy confinement time, the time when fusion can sustain without additional drivers. And this is formalized in so-called Lawson's criterion. In the sun and stars, particle density is achieved via gravitational forces, and you need only about 15 million degrees C, in fact, to sustain fusion. On Earth, of course, the density that could be achieved is considerably lower, which means that the temperature has to be considerably higher, and approximately about 10 times higher than on the sun. And these conditions can be reached in the high temperature plasma, which is confined in a vacuum chamber by high magnetic fields. So why we want to do fusion? I mean, it has little or no environmental impact and produces considerably less activation than fission. There are no risk of critical safety events like the meltdown of the reactor. And it uses small amount of fuel to produce huge amount of energy. So 1 kilogram of fusion fuel, and that's the mixture of deuterium and tritium, would provide requirements for roughly a gigawatt electrical power station for a day. Now, because we need so small amount of fuel, in fact, fusion is actually sustainable, and it is, as this fuel is abundant, at least in one case. In fact, deuterium is a natural hydrogen isotope and is produced on the industrial scale. So basically, there is no shortage of deuterium at all. Unfortunately, tritium exists in nature only in traces, and nowadays it's only produced in heavy water neutral reactor. But the whole philosophy of fusion is that tritium will be actually produced in a so-called breather blanket, which is surrounding the plasma, in the interaction of neutrons with lithium. And blanket will be basically cooled down with lithium, and in those two nuclear reactions, which you can see on the screen, you can actually produce tritium. And the whole idea is that you produce more tritium than you actually use. So basically, you have a sustainable source of energy because you have sustainable fuel. And current reserves of lithium are around 50 million tons, about 3 million tons of lithium-6, which is the most important one in this case. But it also exists in oceans, basically in water, at very low concentration, in fact, of 0.1 ppm, which means it's not commercially viable, but in the future, who knows, maybe it will be also possible. And there are then around 250 billion tons of lithium on Earth. Estimated requirement of a fusion-based 1 gigawatt electrical power station is about 500 kilograms per year. So this is how it actually looks like. The whole thing started about 100 years ago when Cambridge astrophysicist Arthur Eddington proposed a mechanism which actually powers the stars. And unfortunately, as very often happens, the first application was military one, and it was the production of a thermonuclear weapon in the US in 1952. But at the same time, scientists started all over the world, actually started to consider peaceful application of this process as a possible, well, almost unlimited energy source. And quite a few machines were built in the late 40s and 50s, but they couldn't really sustain stable plasma. And the real breakthrough was achieved in the late 1960s in Russia with tokamak T3, which produced the first really quasi-stationary fusion reaction with ion temperatures which were 10 times higher than in any other device. And as a result, many tokamaks were actually built and operated. More than 100 devices were actually operated so far. Most of them in hydrogen and deuterium, but the only two which operated in DT fuel were joint European torus and TFTR. There are, of course, other methods of creating fusion laboratory conditions, and that's inertial fusion energy, where you use small frozen fuel pellets, which are rapidly compressed and heated by either high-power lasers or some other drivers. There are also some other methods, but we're going to concentrate here on tokamaks because that's so far the most developed concept. And the tokamak itself is just shown in this figure here. So you have a donut-shaped plasma, which is confined in a vacuum chamber, not shown here, using toroidal and colloidal field coils. You use central solenoid as a primary transformer circuit, and the plasma itself is a secondary circuit. And when you have many tens of thousands ampere turns in a solenoid, you will produce quite a few millions of amperes of plasma current which are circulating in the torus. To heat the plasma to the desired temperatures, you use either fast neutral beam particles, or you use radio frequency waves or microwaves. And also fusion reaction, it produces alpha particles, which I mentioned at the beginning of my short talk, which can also actually heat the plasma in the tokamak. So today we have three presenters. The first one is Alberto Larte, who is the head of science division of the International Thermonuclear Experimental Reactors, so-called ITER, which is being built in Saint-Paul-le-Durance in France. And he will tell us about the progress on this device. Jiangang Li is the former director of the Institute of Plasma Physics of the Chinese Academy of Sciences in Hefei in China. And he was involved in the development of many fusion devices, well, present one and future ones in China. China has actually probably the most ambitious and the most developed national program. So that's the reason why we are talking about that one. And finally, the third talk is by Gianfranco Federici, who is a program manager of the European Consortium for the Development of Fusion Energy, or so-called Eurofusion, which is coordinating all the fusion efforts in Europe, and who spent many years, in fact, as a department head of the technology department within that consortium. So that was my talk, and I now will stop my sharing and allow Alberto to start with his bit.
Okay. Hello. Thank you for the invitation. So I hope I can share the screen. You see, I think. Do you see the presentation? I have to change the...
Not yet.
Do you see now?
Not
No?
quite.
Yes. Excellent.
Yeah, okay. It arrived. Okay. So thank you very much for this invitation. I'm going to give a short summary of what is the objective of the ITER project and where we are with respect to construction. This is actually a photo of the project itself in its present situation. So the first is to describe the ITER objective, then what are the design features that we have to achieve the objective, and then the origin of ITER, because ITER, besides a scientific endeavor, is also a human endeavor, and then where we are and what are our plans ahead. So the main goal of ITER is to demonstrate the scientific and technical viability of fusion as an energy source for mankind. And this is important. We are trying to address as far as possible all the scientific and technical challenges. There are a few that we cannot do, technical challenges that are left for the future. And I think Giangan and Gianfranco will talk about them. What we are trying to create is a self-sustained plasma, a self-sustained gas that produces fusion reactions. So as Dragoslav said, we plan to fuse deuterium and tritium. To get this gas to fuse, we need to heat it up with the power. So we use up to 50 megawatts of power. Here we are using, most of it actually comes from radio frequency, so similar to a microwave oven, but a very large amount of power. And then this will fuse, produce an alpha particle, helium, that will reheat the mix. And the idea is that this will produce 500 megawatts of power. So these are thermal power. ITER as such does not produce electricity. We just demonstrate that the fusion reaction can self-sustain and can be used for as an energy source, technically and scientifically. As was explained, one of the things that ITER doesn't do and is left for the future is to produce the tritium we consume. Of course, the deuterium can be extracted from the water, but the tritium has to be produced, and as Dragoslav explained, it has to be produced by making the neutron that is produced by fusion to react with lithium. And ITER just will do a proof of principle of this, but actually most of the tritium we will use will come from the available one. Okay, so how do we get this? For this, we have taken as a design the tokamak. So the tokamak is the confinement system that produces the hottest plasma, the highest fusion power so far, as demonstrated, for instance, at JET. We want to create very large magnetic fields because the amount of fusion power that you can create depends on the pressure that the gas has, which depends on the magnetic field you apply. And because of this, we have very large currents we have a lot of magnets, as Dragoslav explained, and the current level is very large because we need to go to very large magnetic fields. Therefore, in order not to consume an infinite amount of electric power, we are using superconducting materials. So we have two types of superconductors depending on the need and the field at which we need to apply. So we have what we call the toroidal field system. Let me put this. I want to highlight, sorry. I think I did a mistake. But the toroidal field system, which is in gray, and the central solenoid, which is made with one type of superconductor that goes to fields of more than 10 Tesla, and the other system, which are in pink, are at a simple superconductor, which can go to typical values of the order of 6 Tesla. Then the vacuum vessel itself, where the gas is contained, is shielded from the neutrons and the interaction of the plasma by what we call the blanket modules, which is where the heat and the neutron energy is deposited, which are in yellow, and they are covered by tungsten because this is the material that can sustain the highest power fluxes and temperature. The power fluxes to the wall, this alpha particle that we create, creates very large power fluxes to the walls, and if we would not reduce them actually in the lower part of ITER, which is what we call the divertor, what we use to exhaust the power, and the helium, the ashes that we produce by fusion, we would get similar heat fluxes to the surface of the sun. So actually we reduce, which is about 50 megawatts per square meter. So we actually reduce this by about a factor of 5. Because the machine is superconducting, it has to be enclosed in a large thermal flask that we call cryostat. And of course, we are equipped with a lot of systems to heat up the gas to 100 million, more than 100 billion degrees, and to measure a lot of the parameters of the gas, the composition, the temperature, the magnetic field in this hot plasma, etc. So we have about 100 parameters that we measure with diagnostics. Now, as I said, this of course, this is just the reactor itself, but the reactor is encased into a reactor building. So the typical dimensions of the reactor are 20 by the order 20 to 30 meters tall by width. And so we have a lot of systems that are required to operate this. Apart from power supplies, etc., we need to also supply the gas into the machine, the deuterium and the tritium, clean it when we pump it out to remove the impurities. And this is what we call the tritium building, which is on the left side of this slide. And on the right side are all the systems to measure plasma parameters, etc. So the very important thing of ITER is that it's not just a physics experiment, it's scientific, but also a technology experiment. So the idea is that after we demonstrate that we can maintain fusion producing energy plasma in ITER. And if we solve the issue related to neutron and the tritium production separately, we should be able in a position to build a fusion power reactor, a demonstration one. Now, ITER has a long history. It was born in 1985 during there was a time with very high tension between the US and in general the NATO and the USSR. And there was a decision, since this was realized that fusion based on magnetic confinement has really no military application, is something that we do for the mankind. At that time, Ronald Reagan and Gorbachev decided to start this project. This project was already, we had several inspirations before of building a tokamak together, many of the world superpowers at the time, and it evolved with more countries that joined this endeavor. So originally the ITER members were Japan, the US, the European Union, and at that time the Soviet Union. Then Russia remained, and then for the construction of the machine itself, China, India, and Korea joined in 2005, actually before 2005. So in 2006, the agreement to build ITER was signed in Paris. The machine is being built in France. So we are actually an international organization like the United Nations, made by these 7 countries. Of course, the European Union is represented by Euratom, so the European Commission, and the ITER responsibility is to be the integrator of the components that we receive. I will explain one thing which makes ITER a bit peculiar as a project, and then to operate the facility. So now, one of the very important things that the components of ITER, most of them are actually provided by the ITER members. So we don't fabricate, ITER does not really fabricate or buys components, only a very small proportion. Most of the components of ITER are built by the ITER member. This is very important because in this way, the knowledge how to build a fusion reactor is shared, and the ITER members have the capability to do it. And the in-kind contribution is divided into parts. So the European Union pays 5/11 and the other members paid 1/11. So in total is of course 1. The people that work here theoretically should be represented by the proportion. In reality, there are some members, like for instance China and Russia, which are very close to the 1/11 proportion. There are others that underfall. And this, as normal, because we are based in Europe, is replenished by Europeans. But there is a project strategy to try to minimize the number of Europeans and also to increase the number of females, which is not very large. As you can see, in total, we are 1,000 people, but there are contractors and companies that are providing services. So on site depends on the activity, but the normal number of people is between 3,000 and 5,000. Now, as I said, very important thing of ITER is that the components are built by all the ITER members. So this means that a lot of problems and complications we have to integrate. Everybody has to. The good thing is that we learn to work together and provide components that fit with each other, that work, and also humanly we form teams of people that collaborate independent of where they come from. So this is, as I said, there is this human part of ITER, which is a kind of world endeavor. But you can see that the components are built by many ITER members. The more complicated ones, like the toroidal field coils, are actually built by all the ITER members except India. There are others which are divided into smaller pieces, depends on the capabilities of the ITER members and the fabrication, the technical and capabilities. And this was divided at the beginning of the ITER project. The idea was that the knowledge, which is very important, all intellectual property is shared, so the design of the ITER system are actually owned by the ITER members, and everybody knows how the machine is built. So the knowledge is not isolated to any specific member. Now, despite this complication, we are able to build, all the ITER members and the ITER organization are able to build very large components. These are the toroidal field coils. They weigh 360 tons. We have 18 of them, and they are very large. So you can see how everybody has done conductor, two ITER members have made actually the interior of the coil, then they have been welded together, and then they have been brought to ITER. Now, this one quite complicated thing is that the fact that the components are built shared by many of the ITER members, you can imagine the logistic problems. This is what the number of transport that have to take place to actually build one of these superconducting coils. So you can see the issue is complex because the components are built in several places, they are put together somewhere else, but it also shows how a worldwide collaboration of this type can actually work. Now we have other components. All the main components of the machine are finished. So here, this is the largest, one of the largest poloidal field coils. This measures about 20 meters. The central solenoid is also one of the strongest magnet in the world that also is being finished now. We have the component. This was made by the US with cable from Japan. The vacuum vessel has been built more or less half of the machine by Korea and half of the machine by Europe. Actually, the machine has 9 of these sectors, so 4 are built by Korea and 5 by Europe. 8 are completed, and we are already them on site, and we are actually installing them. 1 is being completed and will come later this autumn. So the construction site, as I said, apart from the machine itself, which is located in this black building on the right side, it is a large scientific installation. So we have a lot of services to operate the machine, like power supplies, to exhaust the heat, to cool down the magnets to very low temperatures. The magnets are cold to minus 269 degrees to handle the tritium, etc. And we need, of course, a large energy supply. So we have a 400 kilovolt switchyard that connects to the French network. Also, the very largest component we couldn't really transport, and they had to be fabricated on site. And these are at the bottom of this figure, which is what we call the poloidal field winding building. This is a superconducting coil factory that is now basically decommissioned, and we use it as a workshop to test the superconducting coils. But this was this 300-meter long building, and the cryostat workshop, which is where India put together the thermoflask because it's too large to be transported. And here actually you can see some of the components of this cryostat which are waiting to be installed later next year. We have the cryo plant, which is the largest refrigerator of the world in a single unit and can cool down the superconducting coils, which are 10,000 tons to basically near the lowest temperature of the universe. And so in terms of progress, we started assembly of the machine in terms of putting the reactor into the tokamak building in May 2022. And then we have two difficult years because there were some faults in the manufacture of the vacuum vessel. And also we identified the corrosion in some of what we call the thermal shields. These are some parts which are installed in the machine to prevent the heat from the gas and the neutrons and the vacuum vessel itself, which is maintained at 100 degrees C. To go to the superconducting coils, and there was long-term corrosion. This means that the gas that is the very cold gas which is circulating there could actually leak and lead to actually arcs between the superconducting coils. So at that time, when these problems were identified in summer, autumn 2022, the management took the decision to stop the construction of the project, go back, repair the issues, and start again. So this took us 2 years. We solved the issues. We removed all the faulty cooling pipes. We reshaped the vacuum vessel so that it could be then welded properly. And we started back in 2024 assembly of the machine. So we have 2 years that were very difficult for the project because we were fixing mistakes that were accumulated over the past year, some of them influenced by the COVID, I have to say. And then we started, and since then we have gone quite well. So we have now, and I had put this plot, and this is what I sent to Dragoslav on Monday. This is the installation of the 4th vacuum vessel sector. And actually this night, we have installed the fifth one. It is coming here from the crane, and it has been installed this night. So you can see from September to now, we have actually assembled, in terms of sectors, 5 out of 9. So things are really going pretty well. Of course, there are challenges, but we are quite confident that we will be able to build the machine according to the plan. I have to say that in these 2 years that we had of these many difficulties, one of the things what we did was to do a complete rethought of the planning, and the new plan is we try to be more realistic, less optimistic, and to allow for time to correct mistakes, etc., which we didn't do before. And since then, we are actually implemented the plan as planned, or actually earlier than planned. So things are going pretty well. Now, this is our new schedule. As I said, we are keeping this pretty well. So our plan is to actually close the machine, the cryostat, in 2032 towards the end, and start integrated commissioning, what we call in our case to make vacuum, cool down the magnets, and start to do tests to make sure that the machine works in 2033. Then we have an initial phase of about 2 years in which we don't use tritium, and we commission the machine, so we are sure that we can create plasmas, that we can get to this 100 million degrees temperature, that we can produce the magnetic fields, that basically we know what we are doing. So in that sense, ITER would be similar to what is done in most tokamaks today, but at much larger scale. Then we install the final set of components in the machine, and then we start what we call DT operation. So our target is to demonstrate this 500 megawatts fusion power sometime in 2044, which is 10 years from the start of operation, basically. And then we progress further to expand to increase the power, to extend the duration of the production, etc. So with this, I conclude. So as I said, ITER is a challenging project. We had a lot of difficulties in 2022. So in 2023, actually things changed, and since then we are going pretty well. One of the things that we did, as I said, as lesson learned, is that we made a new plan, which is much more realistic. And of course, when things are going very well, but it's not going to be that tomorrow we are to demonstrate the 500 megawatt fusion power. And together with this, of course, we need that the ITER members support, because there is a lot of R&D to be done, the way we are going to operate ITER, the way we shorten the time to get to this Q equal 10, this fusion power amplification factor, the 500 megawatts, etc. So it's not that the research in fusion has to wait now 20 years or 10 years. No, it has to go on, because depending on the results that we find, we will optimize, of course, the way to demonstrate our goal. And with this, I just leave you with a small video that shows how actually, if it runs, which I don't know, yeah, we actually shows the assembly hall of ITER, and how one of these actually sectors, once it is completed, is installed. These are things are, I mean, you see them very fast. They take about 1 day, and this piece weighs about 1,000 tons. So it is not trivial to install, and the components themselves, these toroidal field coils, are aligned to each other to precisions of 0.5 millimeter over 70 meters. The whole thing is kept, the whole room is kept at 22 degrees, so that we are actually very sure we align this very, very well. So you can see how this happened. This was sector 4, and the ones that happened this night is more or less the same, but I don't have the video yet. Thank you.
Thank you very much, Roberto. I think if there are any questions or any discussions, we're going to leave it for the end. In fact, so
Okay.
I think the next one, I think we'll go to the Jiankang Li, who I can see just started screen sharing, and he's going to tell us about the progress in China, which has the most ambitious fusion program of any country in the world. Off you go, Jiankang. We can't hear you. It appears that you're muted.
First of all, thanks for invitation. Let me share the activity in China, especially for the superconducting tokamak fusion development in China. And not sure why it's not moving. Oh, here. Yes, actually, the superconducting program starting in last century in 90s. And we get T7, the old Russian superconducting device from Russia, and with help from Russian scientists and also engineer, and took us about 3.5 years to reconstruct these machines. And we spent about nearly 18 years for operate these machines. And you can see the former director, Professor Huo, he is initiate the Chinese superconducting program. And we use this tokamak to not only to do the experiment, but mainly as a training start. There are about more than 100,000 shots has been fired on these machines. And just as I'm about to say, in year 2006, we formally joined the ITERs. And after we joined the ITER, and we have the Chinese, roadmap. So we spent nearly 10 years to follow this roadmap. After we joined ITER, we wish we can build a Chinese fusion engineering testing reactor, which cover the fusion power from 500, 200 megawatt to the 1 gigawatt. And at the year around 250, we can start a commercial power plant. This is a roadmap. And actually, we carry out this roadmap for the past nearly 15 years by using the yeast experimental tokamak. And yeast acquired as more than 30 megawatt fusion powers and with a megampere current. But mainly we focused on the steady state operations. Year by years, and we achieved the steady state repeatable plasmas. And a few years ago, we had the repeatable HMO, which can last for 400 seconds. And this is very reproducible. And last year, we even extended porcelain to 1,000 seconds. And end of last year, we started upgrade and to change all these internal components, enhance the cooling capacity, and to the full more, and also aiming for even longer porcelain hours operations and prepare for the experiment for the next step. And nearly 10 years ago, we started Chinese fusion engineering testing reactor program. This is by two parts. First is designing. You see the main goal for these machines is trying to establish the fusion power around 1,000 megawatts, duty cycle 50, with a Q over 10 to 30 after ITERs, with the tritium breeding over unities. And we had the two stage for this designing, and physical designing and engineering designing by large teams. You can see the team is nearly 800 people enjoying, spent 8 years, 3 years concept design, and 5 years engineering design. So you can see the 5 group has working on it. And so this is the main parameters, 7.2 meters major radius, and also the field is higher than ITERs, 6.5, and with a higher the volt flux, and even run by hybrid scenario, this can be hour operations. And this is the layout for the engineering designing, and all the detail has been assembled by the international and domestic expert group. But whether we can do it, so in the 6 years ago, end of this 2019, the Chinese government initiated a program called Comprehensive Research Facility for Fusion Technology, CRAF project, and do the large scale R&D for these CFETRs. And this is something not only to learn from ITER, but also beyond. So we would like to master all the technology from ITER, but also trying to get some new development beyond the ITERs for demo type machines, and also training next generation of the fusion scientists, engineer, and managers. And you see a list of the system and facility in the craft project is in about 20 subsystems, including material, conductor, magnet testing facility, and also the ITC central solenoid coils and the full-cell TF coils, cryogenic system, power supply system, and also testing for material. We built a linear machine for steady state hours operation or days operation, like PSI magnet, and also the heating and current drive. Heating and drive, including 4 of them, ECRH, neutral beam, low hybrid, and ICF, and also the blanket and diverter facility, including vacuum vessel and the remote handling. All the things are supposed to be finished within 5.5 years. We are about 1 year delay for this. We're still not finished, but we almost get there. You can see nearly 90% of the project has been finished. And you see this is only a few of them due to the time limit. It's a TF coil testing facility, neutral beam. We already get a few 100-second, 2 megawatt beam, and also the blanket. We are trying the supercritical CO2 together with the lithium lead for this blanket loop. And also this is a vacuum vessel and also the remote handling testing facility. And they are training the robust for the automatic welding, cutting, and the remote. Within the heating and drive, most of these components now can be made in China. This is the PSI testing facility and also the central solenoid testing facilities. I show 2 examples. First is the coil. The TF coil is the full size. And the storage of this TF coil is about 3 times the ITER. And so the field on this magnet is 14.5 Teslas. And as a comparison, this is the best coils, the 2 of best coils, and this is CFEDR, the TF coils. You can see the difference. And another advanced development is the diverters. We use the new material for the columnar, the tungsten, and ODS copper, and also the ODS for the whole blanket. This is the full size of the blanket. All these things have been fully tested up to 20 megawatt meter square, the power handling capacities. And also the big robust has been developed. Use the manipulator can replace the damaged component. I only give you 1 example for the RCH. And the RCH, each of the RCF generator can deliver 1.5 megawatts. And we tested from the 40 to 80 megahertz wide band, and each of these frequency has been fully tested, meet the the more than 2.5. We are combining 2 generators into the 1 transmission line go to the antennas. So all the component has been fully developed in China. And in the year 2020, we to relook our whole roadmap, we find we short machines which can bring the burning plasma before it start. So, and we would like to have a new machine called the burning plasma experiment superconducting tokamak best, which can get early stage to have a burning plasma experiment before ITERs. And so the mission for the best is trying to to have a facility and for the Q over unity for steady state, and we can testing the full cycle for the tritium breeding, especially for the fuel inventory and tritium breedings. And for the short pulse, a few seconds to a few 10 seconds, we can explore the Q over 5. And this machine has been proposed in the year 2022. We started designing, and the objective for the best, not only to do the burning plasma experiment, but also trying to further development the key technology for the future demo reactors, including superconducting, diverter, diagnostic control, and the other things. And after 2 years designing, and we had this baseline scenario for Q1, with about 20 to 40 megawatt fusion power, and also for Q5, around 100 megawatt fusion powers. And this is scenario is our baseline. And we're starting construction in the year February year 24. So you can see we dig a hole on this new floor in the February 28, 2 years ago. Now the building is nearly finished, and nearly 1/3 of TF coil, most of the PF coil, and half of vacuum vessel has been finished. And the coil, the bottom coil for the PF7 has been fully tested, and this is the PF5 coil in the installations. And at the moment, we had a very good cooperation with Eurofusion. And thanks to our Eurofusion colleagues, gave a very strong support, not only for review designing, but joining us for the research plan. This is our joint research plan, which we released last year. And we have the very tough schedules. We're starting construction, as I say, in the February 28, 24, 2 years ago, and we only had 3.5 years. We are looking forward to have this machine can be finished assembly end of next year. Now, and so we installed already 3 PF coils, and the crash start bottom is already there. 2 vacuum vessel is there, and TF coil are going to be tested next month for 2 testing. All the coil are going to be tested, which is supposed to be finished around the end of this year. So, and you can see after we finish the installations, we hope can see that in the year 2028 to have the 1 year's DD operations. Then with another 2 or 3 years, we are going to have a tritium DT operations. So we certainly to have a long pulse Q over unity before 30s. So the schedule most likely is the most challenging things to us. And at the moment, we also doing the designing for the CFTR, but originally we aiming only 1.5 gigawatts by request of the government, and we need net electricity over 200 megawatts. For doing that, we need a high fusion power. So for the past 1.5 years, we upgrade our designing from CFE TR, T is testing, to DR. D is demo for electricity generations. And at the moment, last month, we finished the second round, the international assessment chaired by Alberta. And you can see we enlarge a little bit the machine from 7.2 to 8 meters. So the fusion power from the 1 gigawatt to about 3 gigawatts. And the current is from 15 megampere to 20. So with this new scenario, and we have this confidence, we can have more than 200 megawatt net electricity, even 500 megawatt electricity. And so we already find a few candidate sites, but the primary site is in Hefei, is near a lake, near a lake. And this is a drawing is made by designers. And hopefully we wish and we can start sometime next years. And this machine, we are looking for 10 years construction time, 10-year construction time. So this is roughly all this development for the superconducting approach. Parallel in China, we also had a program for the material, for the tritium plant, and also for the component testing, which are not in this talk. As a summary, for the past 5 years, there's some progress, and to me, I think this progress is quite good, and not only for East Craft, but also for CFEDR together with the best construction. And as I said, East finished the upgrade with the high power, even high powers, and fully active coated tungsten wire, and also the large plasma size to supporting the best and also ITER in the futures. And end of this year's, all this program, the 20 subsystems, will be finished for the craft project. And next month, the TF coil will be starting cooling, and within 2 months, we are going to have a fully testing for these TF coils. And so this relatively challenge and whether we can finish the construction for the best. But anyway, for next 5 years will be key step. Consists a joint effort from East, Best, Craft, and we wish within 5 years, within the time slot, we can start construction of the CFETR. And that's for my talk. Thanks for your attention.
Thank you very much, Yang, but your video is off, so we can't see you. But thank you very much in any case. So I think we've seen quite some progress, well, both in France, but also in China. And now we have Gianfranco, in fact, to put us down to earth, in fact, to tell us that it's not all hunky-dory as it looks like, because to get to the real commercial plant, which will be commercially viable, in fact, there are quite a few things to be solved. So off you go, Gianfranco.
Thank you. Do you all see my presentation?
Yes, we do.
Okay, first of all, thank you for the invitation, and thank you for putting me at the very end of the list, because the previous speaker and your introduction are very important for me to present. So I was asked to basically address what are the gaps which has to be overcome beyond ITER and the other burning plasma experiment which are being realized around the world. So I would like to start with the key takeaway. Fusion commercialization is not around the corner, as many claim. Investment in infrastructure are needed to solve remaining technical obstacles and not just make unrealistic promises. There is a need to realign and accelerate fusion towards important strategic objectives. ITER mission is fundamental, and so is the importance of additional burning plasma experiments, which are realized in China and in the US. But there are still several technology gaps with fusion core nuclear technology, which are critical for the harnessing of fusion power. This will not be done either by ITER or BEST, or only marginally. Europe is about to propose an ambitious fusion strategy to address the gaps which are going around the problem of extracting tritium from a fuel cycle. I think we need to establish a more resilient supply chain. We need to involve industry more effectively. I think China is doing it very successfully, and so is the US. In Europe, we are not yet there. But we need to be able to attract companies in a competitive way, and we must highlight opportunity to create partnership. At the moment, industry has been contributing to the fusion development in form of supplier. Now, I welcome very much the establishment of startup because they are actually trying to generate a different type of business case. But we need to exploit all opportunities to realign public and private sectors. And we need, more importantly, to attract, educate, and train a new generation of engineers, scientists, and fusion leaders. I would like to remind you a statement which has been made by a famous physicist: for a technology to succeed, reality must take precedence over public relation and politics, because you cannot fool Mother Nature. This has been said and proven many times, has been said by Richard Feynman. Now, let me go down to my presentation. Now, what you see on this slide are the key differences between existing devices which are being built and future fusion power devices. I think there is still a divergence of opinion on how to move towards the fusion power devices. Here we are emphasizing the solution of the tokamak, but there are alternative confinement way within magnetic, but they have to resolve the same problems. And because I think most of these issues are common to all major nuclear fusion facility after ITER. So ITER and BEST are experimental devices with some physics and technology development missions. For a fusion power plant, you need to be able to achieve a relevant level of plant availability. So your machine must work when needed. So the issue of component reliability and remote maintenance, if something goes wrong, are very important. ITER, so BEST, doesn't have a tritium breeding requirement. So this machine can rely on external supply of tritium, which are very limited, but they are sufficient to operate this facility. In the case of a future fusion power device, you need to have the function of breeding as a fundamental function of the fusion reactor. So a reactor must produce its own fuel. ITER, like BEST, use conventional stainless steel structure for the vessel component. This is not adequate for a reactor because the level of nuclear fluence, neutron fluence, is inadequate for a steel. So we are using more resistant materials which are not fully developed, and they have shortcomings. So far, all the devices have been presented to you. They have very modest lifetime fluence, typically less than 1 dPa. A dPa is a displacement per atoms. It tells you how much the machine will operate to achieve its lifetime. In a reactor, you have to increase this at least of 2 orders of magnitude. So we go to 100 dPa. So this will lead to significant damage from the neutrons, and you have to guarantee the structural integrity of the machine. The machine cannot be breaking on parts which are permanent. And very important, and not appreciated, in order to extract power from these devices, you need to have a cooling medium that, in the case of ITER and BEST, is water at low temperature. For a reactor, you need to go to high temperature, high pressure coolants, either water or gas. And this is a quite complex design practice required to overcompensate for this. So the points on the right-hand side are very big challenges. I'll go back to this in a minute. I think we are exploiting here what we thought when Reagan and Gorbachev met in 1985 and T3 delivered the results. The more benign option was to use deuterium-tritium reactions, which has very challenging, but there are others. So at the moment, we think DT is the most mature. So you have to be able to use tritium and to produce tritium, and tritium is very scarce. Actually, I believe that tritium supply and use is a major problem for future fusion developments. First, the tritium consumption in a DT fusion reactor is huge. Typically, for 1 gigawatt of fusion power, you burn 55 kilograms of tritium for full power year. And at the moment, the amount of tritium which is available for non-military purposes is around 30 kilograms, and is tritium which is primarily produced by CANDU reactors as a byproduct. And this is a quantity which is subject to be reduced because tritium is not stable. It decays, typically decays 5.5% per year. So we have to hope that the Canadian and the Koreans are going to extend the lifetime of this reactor. Otherwise, we are going to run out of tritium. And ITER and BEST will contribute to the drop of the tritium available to start the supply of a reactor. So what are the 5 challenges from my point of view? And as I said, I have some experience with this matter because I spent all my professional career working in fusion. I'm a nuclear engineer, though. But in the country where I was coming from, nuclear has been considered politically incorrect. So 5 challenges. Tritium breeding. We need to be able to produce tritium. And as it was said earlier, tritium is typically produced by surrounding the plasma with a system which is called the blanket, where there is a mix of various materials, lithium-bearing materials, where the neutrons deposit their energy and the heat, and this is extracted, both tritium and heat, and converted. We are still dealing with having a problem, which is the power, because remember, a fusion reaction leads to neutrons, but it also leads to charged particles, the alpha particle in the scheme of the regular CIEC. So the divertor is a component where there's going to be a lot of surface heat and still remain an issue. ITER has found a solution, BEST has found a solution, but whether this solution works for a fusion power reactor, there's still a question mark. We need to improve our way to access, repair, and remove the component which will unavoidably either be damaged or needs to be replaced. We are struggling to develop more resilient structural materials because the one that we have, which has required 30 years of R&D, are not perfect. They embrittle at low temperature and they lose mechanical strength at high temperature. And we have to develop systems which are reliable and pay more attention to plant availability. So here I repeat a bit what I said. The tritium breeding blanket and fuel cycle is the big one. If you don't know how to do this, fusion will never be able to reach the major league. Independent whether it's a tokamak or a stellarator, a DT requires having the capability to produce and use the tritium that the reactor produces. So you need to have, from the very beginning of operation, a blanket system which is going to be able to generate a sufficient amount of tritium. We experts, we quantify this with a parameter which is called the tritium breeding ratio. We have to consume a large amount of tritium by setting this parameter to be greater than 1. The truth is that we have not yet either identified a concept which is a winner or built and test the concept which is a winner. ITER, like BEST, will be acting as test beds of concepts which still have to develop and improve. And their testing will be very marginal. So we do see a need to start either alone or together with other parties, a serious breeding blanket and development and testing a qualification program. And Europe, in this regard, is exploring some sort of dedicated solution to enable this testing a level of fluence and flux which are needed. RAMI, reliability, availability, maintainability, and inspectability need to be addressed. The availability is defined typically as the ratio between the mean time between failure divided by the mean time between failure plus the replacement time. So if you want to have a high availability, you have to ensure that component A doesn't break, or it breaks very rarely, and you can repair it very quickly. Neither things we have learned to do it very effectively in fusion so far. We have remote maintenance capability. We have components which do not break, but the condition in a fusion power reactor are going to be different. Remote maintenance is a huge problem. I think JET has been sort of pioneering in this area, and they have been able to achieve various configurations, various levels of fantastic performance, but we need to put the ship into the battle and take it out several times, and this is not trivial. The diverter I mentioned, I think there is a huge progress thanks to ITER R&D, and now thanks to follow-up R&D done in other countries. We are able to reach a magic limit, which is 20 mega per square meter for a water-cooled diverter. But these solutions are very marginal for demo or fusion power reactors. We are looking into advanced solutions, but we see integration with some of these novel solutions very challenging, both in terms of geometry and in terms of materials. We are in Europe building a dedicated facility, which is called the Divertor Test Tokamak in Frascati, to further explore the problem of the heat flux. And the structural materials. Operating structural materials, we have a very narrow window because there are mechanisms of failure, lifetime, which have to overcome. And remember, developing material is a business which requires huge investments and long times. We are in Europe constructing a specific neutron irradiation facility, which is called WAAS, to qualify structural materials at level of flux and energy spectrum, which is typical of fusion reaction. But it takes time and money. There is another showstopper, which I call non-technical, which ITER has proven to be. Cost remains a significant barrier to fusion progress. I think the ITER Director General has been advocating this point in various occasions recently. I think the cost associated with building and operating ITER has shown to be an order of magnitude higher than what is considered desirable for widespread adoption. I think the root cause of these high costs are non-technical. You have seen the organizational complexity and political constraint of the ITER organization, which do not exist in the Chinese organization, has led to the cost of ITER levitating. But we have to take care, and lessons learned from the ITER manufacturing experience, that we need to learn on how to prioritize the cost reduction from the very beginning. And in order to do this, we have to get industry in the business as soon as possible, because very often manufacturing reliability, which are not reflecting in designing choices, we have to avoid over-specification that lead to unnecessary expenses. And I think we have to try to do it together. By reducing the size of the device doesn't necessarily reduce the cost. And this has been proven. I think what we need to do is to simplify the system interfaces and allow adequate space for assembly and maintenance system. Smaller is not always cheaper, because whenever you try to make smaller things, then you are going to propagate. Issue and design changes are required. I conclude my talk by reminding you that the previous two presentations have confirmed that there has been significant advances in physics, materials, and manufacturing during the last 20 years. ITER and other DT devices in construction are crucial for the validation of physics and part of the technology for the next step. Designing and constructing ITER necessitated extensive R&D, which has been characterized by wide-ranging long-term international collaboration and major innovation. I think we have to make available to all the world the lessons learned from ITER, and in this regard, I am involved with other experts in preparing a book. Actually, there are two books on the ITER Engineering Basis Handbook. So you see the link here. When you go to this link, you see already some chapter available. The ITER legacy is critical for the design of any other future machine. I think Jiangang Li and his team has learned this legacy by being a fundamental partner of ITER. But there are others which are not really familiar with ITER design, and they have to understand that ITER is like that. And it cost a lot of time to design because we found problems. And as you see here, we have device that spans across generations. I think we have to be able to transfer knowledge between generations. And we have to make this logic available to everyone. So to conclude, this is my opinion, you can ignore it. To me, a credible fusion strategy must address upfront the gaps of the breeding blanket and fuel cycle. In my perception, there's too much emphasis and focus right now on magnets with a push towards high temperature superconductor. It's an important development, but it's not a showstopper. Magnets have been built, and there's been examples given in this conference, in this webinar, that we know how to build powerful, large size, high field magnets. I think we need to have an effort to develop new technology facility for testing breeding blanket under high neutron irradiation, explore new plasma scenario in order to alleviate the power exhaust and consolidate all the manufacturing site from ITER. And RAMI, reliability, availability, maintainability, and inspectability must be central and addressed with the same rigor, if not larger, which has been given to plasma physics. Thank you very much.
Thank you very much, Gianfranco. It is an eye-opener when you talk about it. I remember I've been to many fusion technology conferences and always avoiding blankets. It's something boring, but obviously without them, we can just forget about everything that we did in our life. So I can't see actually any question from the audience. I know that there are some 30 people, in fact, attending at the moment. So we can just start with some discussions which I prepared by looking at your presentations in advance. And start with knowledge transfer and so on for the future generation and how to keep it. The tendency of engineers is when they design something, they want to go to another project. Rarely they want to stay, in fact, within the project that they designed. And it's probably quite hard, in fact, to convince them that there is still something interesting beyond design and beyond testing. I mean, we proved that on JET by using some engineers, in fact, in the operation, which they enjoyed thoroughly. But the problem with some of the machines, at least I can see with ITER, is, Alberto, you mentioned that your average age at the moment is 48 years.
Yes.
Which means that the start of research operation, it will be 56 years, which is 4 years before the retirement on ITER, which is compulsory, I think, at around 60, yeah?
No, we don't have a retirement age. But anyway, I think this is not a problem of legal. I think the problem that you raise is a right one, which is that we have a generation gap in the sense that, as you know yourself, the generation that has run the large tokamaks of the past, many of them, they have a lot of knowledge and they are retiring. That is why I think, in my view, actually, this is something we are studying ITER. And the new machines that are coming online, like JT60, like BEST, are actually very, very important because this is the opportunity for our generation to pass the knowledge to the new one. So not only they are important, I think, at the level of the countries that are developed them, but I think also at the world level. Otherwise, we will have a big loss of knowledge, and then to rebuild it is, to learn in a large machine is the mistakes are very serious. You can lose a lot of, it's not that you are going to go disaster, but you make mistakes and you lose a lot of operational time. And in these very large devices, this is a very, very expensive thing. So I think the type of a strategy which, for instance, China has, where there are a lot of projects, one after the other, of increasing size, is actually the correct one. And I think everybody and Japan, all the ITER members who try to be involved in this, and there are collaborations between Eurofusion, etc., because otherwise we face a big generation gap, and this will be very difficult when ITER starts operating.
My feeling that actually China has a pretty good policy at the moment, because from what I heard from my colleagues from JET, you have loads of PhD students actually running the stuff at East and dealing with many different things. Is that the case, Zhang Gangli? In fact, I think you are basically educated students in plasma physics and fusion. And in Europe, we only have maybe few courses which are dealing with it. As far as I know, there is one in York. There is a column plasma physics school. I don't know. What's the situation in Italy? What's the situation in Germany or France? Can anybody comment on that?
Yes, of course. I mean, Eurofusion has a very strong education and training program.
Yeah.
We actually provide and support large investment toward this. And we are now keeping up with the pace because we are developing e-learning platform. But I think we are very sensitive to educating and training people. So far, we have been attracting more scientists than engineers.
Yeah.
Because the reason that Alberto said, I mean, we have been very sort of reluctant to put new project on the table. We got everything focused on ITER. To get in, and engineering is a practice where there is a lot of competition.
Yeah.
So I think if Europe wants to keep competition while defending ITER and using ITER as an ideal sort of a place to be trained, because this is what the Director General thinks, and I think he's right. We have to provide this new engineer also in Europe with opportunity. Otherwise, we send them all to China. I will be very happy to provide them with, I think, an engineer. I mean, a fusion engineer. Well, now there's a geopolitical situation which has been developed recently, which I'm not very happy with, because those like me who have been working in ITER has learned on how to abandon geopolitical barriers.
Yep.
And I think this is the main concern that I have. Europe is fragmented. We are sort of bringing back national policy, national agenda. And we have forgotten that in 1980, and I think you said it, that when there was a crisis, Europe had the courage to benefit from the large investment made available thanks to the embargo to have a European project.
Yep.
So I think China doesn't have this. China is, in a sense, able to retain much more cohesion. There are regional disputes, but it's much less than in Europe.
Yes, China get a benefit from the international cooperation starting from, from Russian. And later on, we learn a lot from ITER, from all the facility, and even from US. And I think the Gianfranco is correct. We not only need to transfer knowledge to the next generation, but also we have to get more and more young talent to be interested and get involved. And especially recently, every field moving fast. How you can absorb the young talent into the fusions? In China, they changed a lot. When I was a student, the most favorable subject is physics. Physics can the best. Now the mathematics even more popular than the physics. So you can see every field, especially the AI incoming. You need to get people, especially young talented people, to be interested, to be get involved, to be taking part on it. So from the beginning of this fusion program 50 years ago, we had the summer school. So this year is already 45 years summer school. Every year we have more than 250 students and to be on this school. For example, even our institute, and every year we have nearly 300 new students, half PhD, half master. and which is still a large gap. I think the short of the personnel, the gap even bigger than technology and science. You know, the ITER only had 1,000. For next step, we need 10,000. 10,000. Where is 10,000 come from?
Yeah.
Especially you need at least 10 years for trainings. So that's why, and we are starting from especially these 2 years, we're trying to get new fusion school in the top 10 universities. We already had four school established in 2 years. And by enhanced international cooperations, we get excellent teacher like Alberto, Gianfranco. They are all these teachers when they come to China. A lot of students keep asking questions. And meanwhile, we are wish to open all the facility, not only best craft to the international communities. We get benefit from the international community. We like get the returns to open all the facility to our international community, to the peoples. And when a young guy, a young talent, join the different program, for example, in ITER, in JT60, in JET, I think the whole community can get benefit and moving forward together. So we are going to continuously doing this way. So not only the summer school for the physics, but from this year, we like to have a new series for technology, and to training the student. I think this is important.
Okay, thank you. Yes, Neshkovich has the question because you raised the hand, or am I right or not?
Okay, yes, you're right. I have a question for Gianfranco Federici. I have noticed a small-scale fusion energy project going on in Malaga, Washington, USA. The company behind it is Helion Energy, and its aim is to commission a 50 megawatt fusion facility by 2028. Do you know more about the project? And if yes, what do you think about their announcement of supplying electricity to Microsoft data centers in a year and a half, believe it or not?
The answer is no comment. I'm sorry.
My comment is impossible.
I have
No
expected that. That's why I have asked, because there are information about that throughout the world on the social media.
Yes, the point is, I mean, social media, well, do you believe every single word that Mr. Trump says? And he's on social media all the time. When you look at it's private companies which actually probably are looking for investors and so on, and they can promise anything basically, and if they don't do it, in fact, in 2 years, investors are going to lose money and so on. In the big project like the ones that we used to work, and all of you still work, it's the government which is behind it, and you have to be more realistic. Even if there is a desire, I must admit, as a scientist and engineers, we were always slightly more optimistic than necessary and promising things which just maybe could be done if everything goes perfect, but life is not perfect.
May I mean, no comments, and I would like to ask you to read the sentence I put on the slide number 2 on the bottom, which I repeat.
Mr. Payman.
For a technology to be successful, public relation on politics and promising do not work.
Yeah.
I think I wish them luck.
We should wish them luck, all of them, but
I am exactly, and I think here we have to distinguish. I think private intervention in fusion is important.
Yes.
But in order to access private investment, they have to make promises. They have to generate a business case.
Yes.
So I think the challenge that we all have now is to realign somehow with them. It's not easy to talk to them.
Yeah.
Some of them are not so far away from us. I think most of them have understood that without a breathing blanket, they don't go anywhere. So I think here we have to, ITER is been hosting regularly for the last 3 years a forum for discussion. I think they are learning learning. But I think it's certainly an important technology, but it takes time.
Yeah.
With or without artificial intelligence.
Yeah. To
One
me,
more
I
thing
think, sorry.
So,
To
off
me,
you go.
one thing which I think that I see is that what I think it would be very helpful, because what happens with many of these private initiatives is that actually the people that start them are usually physicists from plasma physics, like me.
Yeah.
And I think they come with new concepts. It's true that some were abandoned, and maybe they should not have done because some of them were abandoned for the wrong reason. So they want to re-explore these concepts and see, because the new concepts, there are not so many. Actually, in the 60s and the 70s, people really tried everything.
Yeah.
And so what they do is they argue that
We all
some of the
remember
reasons.
cold fusion, of course.
Exactly.
In a
So
glass of
people
water.
people argue that some of these concepts were abandoned prematurely because there were issues related to the engineering that at the time could not be well done. Now you have higher magnetic field, etc. So I'm not against this, but it is true that they do very optimistic extrapolations of the future, which is usually in fusion so far have never materialized. But the area where I think private companies could really push fusion is what Gianfranco said, the engineering of systems. Because at the end, even if you have the most brilliant concept in plasma physics, at the end you need to build the reactor. And I think at the end, if we don't develop the technologies of fusion, there are heating technologies, processing technologies, the breathing blanket, etc. If you don't do that, even if you have the best physics idea to produce fusion in the most effective way with the concept that was abandoned and works, and it's okay, I want to build a reactor, and it's okay, now I need 50 years to develop the technology. And this is an area where I think I see there are some of the private companies that are actually going along this direction, but also, for instance, the classical, I would say, nuclear fission engineering could help a lot to develop fusion faster. But what I see, and as Gianfranco said, most of the companies actually go on making very small reactors that will work tomorrow. And maybe the right way to me for investment would be more on the hardcore technology that would allow any reactor, if somebody has a brilliant idea, any reactor to actually become a reactor, go from experiment to a reactor, because that is needed for all the concepts.
Right. I didn't use the Zoom since I retired for about 2 years, and I just found out that there is also a question and answer panel, and there were some questions, in fact, from the people. Can you open them yourself, or should I actually read you what I found?
No, we see it, but there are 4, right?
Yeah, there are 4 or 5, something like that. Yes.
But they are
ITER
not
development.
questions. Yeah.
So the first one is
Okay.
probably for ITER. It says, can you see it, Alberto, or not?
I can say yes. Yes, there is, of course, some pressure. But so far, there is pressure because, of course, as Gianfranco said, the geopolitics now unfortunately impact more the world that we had before, and there is pressure, but so far we have been successful in shielding the pressure, the political pressure to the project, in the sense that because ITER is an international organization, has some privilege. For instance, we can ask for exception for the transfer of goods from Russia to Europe, which could apply if we were in a French, because Italy as such is actually not France. It's a bit like an embassy. It's a piece of land in somebody's country.
Yeah.
And so this at the moment makes the procedures long, because you have to ask for an exception to the French government, that asks for an exception to the European Commission, but has not stopped the project. So it makes life more complicated. But so far, all the ITER members remain. They meet regularly. It's probably one of the few places in the world where these people actually meet and talk to each other. And so far, the pressure has increased, has made life a bit more complicated, but has not actually impacted negatively the project.
Okay, thanks, Alberto. The next one is probably just a comment, but then there is another question about our opinion, the difference between tokamak and stellarated technology. Anybody wants to go through it?
If I may, I think we should distinguish between Alien and Stellarator. I mean, Stellarator is an advanced concept which has been demonstrated, and he has some advantages with regard vis-a-vis a tokamak because it is intrinsically steady state.
Yeah.
From the physics point of view, but he still has to demonstrate the ability to achieve this magic triple product that you indicated there, in particular the confinement type and the ion temperature, the primary power exhaust. So I think the developments in Europe are in that direction to invest to clarify this, because the device which has been built in Germany has given quite a lot of progress, but they still need to pin down. From the technology point of view, engineering point of view, I think, if you want my opinion, and I think you find this written in the ITER book, a stellarator is not simpler than a tokamak. Actually, is even more complicated.
More complicated. Like looking at
It's
the
even
core.
more complicated. Now, it is true that there are tremendous progress on the magnets, but access in the machine, alignment it's not obvious. So I think toroidal configuration are complicated. So I don't see any benefit. I think here there is and this is not good in my view, because I think it's important that we exploit further the stellarator. But to have a decree that the next power plant will be a stellarator is not okay. I think we should all together work for the development and testing of a breathing blanket. And because this is, at the moment, there is too much emphasis in either a stellarator or a tokamak. There are two churches, two different religions. And fine. But I mean, I think we have to work on the commonalities and address the commonalities, because I think, yes, stellarator might have some benefits, but it might not turn out to be so easy either. So anyhow, I think it's, but they have a much more realistic development plan. So I think the stellarator has a long way to go to prove that they are as good as tokamaks in confining, although if it is true, it's much better. But technology and engineering,
And there was a question about this energy returned over energy invested, which I don't quite understand, which is abbreviated by EROI. Do you know anything about it? I don't know exactly what does it mean.
I think this maybe is end of life. How much you invest in building a facility versus how much it produces integral, I think. But of course, ITER doesn't perform very well because it is an experiment. So the total amount of energy we will produce is not very large. This is clear. Yes. I guess that there maybe Yang and Lee with the CFVDR, maybe this is where you start to see, because it is true that you need a lot of energy to build up the superconducting core. This is true.
Yes, I think this question may be too early to answer, because you haven't for the next step. Even, for example, Gianfranco mentioned the 5 challenge. Even the blanket, how much it costs, we don't know. But to our designing, and we understand fusion, and for tokamak reactors, we need 500 to 600 megawatt minimum for drive the plant. So this is huge compared with fissions. And in that sense, is a compact, small, high field cannot work. We need relatively large machines, even rather than, for example, 4 or 5 gigawatt fusion power. You can get 1.5 gigawatt net electricity. According to the Chinese fission reactors experience, 1.5 gigawatt net is the most cost effective not large and not small. Otherwise, economically, you don't get very good benefit from the market. And I think the similar to the fusions. So small, compact, high field, not fit the real reactor for the future.
If I may add a comment here, I have been exposed to, and I think the person in the audience, there is a tendency to believe small, cheap, and fast. Small is cheap. Well, ITER is 6 meters because it's the only way you can achieve the requirement that was set for this facility, okay? Which is not a disposable facility. It's not that you do a shot, it breaks, you take it away. I think here a facility which has to be a size. We demonstrated in Europe that if you push the field up, the magnetic field, you can reduce the size, but not much, because the structures which are required to compensate for the higher forces, the forces in the coil scales with the square of the field, make the machine bigger, okay? Now, I think what the audience should understand that for somebody who is trying to commercialize, the only thing we can commercialize here is electricity, okay? So the cost of electricity at the end has to be competitive. And the cost of electricity, whether it's made by nuclear fission, is determined by the capex, the cost of the plant, which in the case of fusion is very high, and the opex, the operating cost. Now, the availability of the plant is the lower the availability, the higher is the cost. So I think commercialization should not really be bogged down with the size. It should be bogged down to create a reliable system. Small size make the problem of the power exhaust impossible to manage. So it means that if you operate this plant, the diverter will break very many times and your availability will go down. So at the end, if you follow this route, the commercial cost of electricity will be very high. So I think here there is a tendency to use the size to measure the cost of the device, but this is not what we are trying to do. We are trying to do a source of electricity which is a reliable, safe, and feasible. Anyhow,
Can I make a short comment here? I think the problem, and I think this is one of the things that is very important for ITER, is that the idea of ITER and also BEST or of the CAVDR is that you provide an integrated solution to the problem. And of course, we know that for specific goals, you can cut corners. So this is something that, Dragoslav, we did in JET in the 90s by using carbon, etc. So you can get solutions to a specific problem. You can put a very nice plot in a plot. And then you say, okay, now I want to maintain this for 1,000 seconds. You say, no, sorry, this works for a 0.3 second. And I think this is, to me, part of the problem, that some of the solutions which are being proposed to go faster to a specific goal can go very fast. The problem is that you leave all the other problems unanswered, and this is usually left for the next generation. So at the end, it's not so clear to me that you will get, if you do these steps which are fast and small, it's not so clear to me that you will end up in the same, in the answer actually in a shorter time, because you need to do many steps. And we know this, we have all personal experience on this. And I think this is not really the way to advance fusion. It looks as you advance because you achieve a target faster than other ways, but then you leave also many answers, also so many things unanswered that at the end of the day, it's not so clear you end up to the solution.
Yeah, and it's not only that, in fact. I mean, if the machine is small, it doesn't mean that you don't need the full infrastructure which you need for the big machine, except it's just slightly smaller. But you might need a tritium plant, you might need helium liquefiers, you need power supplies, you need everything basically. It's just slightly smaller, but it's not less complex. I would like only to make one comment, which I think is coming from my operation experience, in fact, in running JET for the last 10, 12 years or whatever. non-active phase of ITER, if I look at your chart, is probably about 1 year.
2 years, 2 years. It's 27 months, actually.
Your DD phase is already active phase because the amount
Correct.
of neutron you're going to produce will be such that the access to machine will be quite limited. I know that you are under pressure from the others, but my experience is having a longer non-active phase, which means operating in hydrogen, until
Yeah.
you prove that
Wait.
all remote handling systems are working fine, and use them during the non-active phase to demonstrate that.
Okay, sorry.
And also you have to shake up the components. You have to find out some error. The design errors will actually appear only in operation, not
Actually, maybe I should
installation.
clarify. This phase of 27 months actually only has 6 months of deuterium operation. Most of the operation actually is in hydrogen, as you said.
Yes.
The reason why we do the deuterium operation is because we need to access HVOT in that phase. But actually, we do the minimum operation possible to achieve the. Actually, we do the minimum operation possible in deuterium because of the activation problem. So, in fact, we do what you said, and this is actually an issue because, as you said, if we have a problem, we will need to wait some time to get into the vessel.
I mean, it's probably the same thing with BEST, I would assume. Jiangang, do you plan any non-active operation initially? Just to
Yes,
shake
of
off the
course.
machine a bit.
About 1 year. 1 year.
Okay, fine. Well, my preference will be that it's longer, but your money providers probably wouldn't like that. But that's my experience. A longer non-active phase is actually quite fine. Neshkovic, you have a question,
yes.
and probably we have to wrap it up at the moment because we are already running 10 minutes over time.
Yes. Well, I think we should conclude the meeting. First, a message to the audience. The presentations, as well as the recording of the whole meeting, will be posted on the World Academy website page events. Not immediately, but it'll happen soon. And second, I would like to thank very much the speakers and the moderator on behalf of the organizer, the Earth Humanity Coalition, the World Academy of Art and Science, and the Club of Rome. Thank you very, very much. It was, for my opinion, is an excellent meeting. Thank you.
Thank you. Thank you very much.
Thank you very much.
Thank
Thank
you.
you all.
Bye-bye.
Bye-bye. Thanks.
See you
Have
at
a
some
good day.
point.
Thank you.
Bye then.
Bye.